a restless planet beneath us. Settle in, breathe a little deeper, let the quiet of the moment wrap around you. Tonight, we're drifting into a gentle exploration of one of Earth's most intriguing behaviors, the trembling, stretching, and shifting that occasionally reminds us that the ground beneath our feet is alive. This is not a tale meant to alarm you, but rather to guide you slowly toward a sense of awe. Because within every tremor, every distant rumble, and every whisper of movement deep below, the planet is speaking in its own ancient language. Even now, as you rest, the surface beneath you is not entirely still. You cannot feel it, of course. The motions are far too slow. But the continents themselves are on a journey, gliding across the planet's surface like immense rafts, floating on a sea of warm, slowly moving rock. This silent drift is the stage on which earthquakes are born. Pressures build over years and centuries, quietly accumulating until one day the strain becomes too much and the earth releases it in a brief but powerful burst of motion. To understand earthquakes is to understand the Earth's constant need to rearrange itself. The outer layer of the planet is not a single unbroken shell. Instead, it's divided into vast slabs known as tectonic plates. These plates push together, slide past each other, and sometimes pull apart, reshaping the surface in slow, deliberate motion. Their interactions sculpt the landscapes we recognize: the towering mountain ranges, the deep ocean trenches, the valleys that cradle rivers, and the coastlines where land meets sea. When two plates press toward each other, something remarkable happens. The crust crumples and folds, rising skyward to form mountains. But this grand act of creation is rarely smooth. Pressure builds until rocks suddenly give way, jerking forward in a rapid motion that travels outward as seismic waves. We know this sudden slip as an earthquake, but the event is really just a moment in a much longer story. The ongoing choreography of Earth's restless surface. Even the quietest regions, far from plate boundaries, hold memories of ancient forces. Faults, like old scars in the crust, can store tension for centuries before releasing it unexpectedly. That is why earthquakes sometimes strike areas where people have long forgotten that the earth can move. The planet remembers even when humans forget. Though we often focus on destruction when earthquakes are mentioned, it is helpful to step back and see the larger perspective. Earthquakes are not simply disasters. They are processes that shape continents, lift mountains, renew landscapes, and maintain geological balance. Without them, our world would be strangely static. No towering Himalayas, no Andes brushing the sky, no dynamic coastlines sculpted by shifting ground. Earthquakes, in their way, help sustain the vibrant and ever-changing planet we call home. This journey into the hidden workings of the Earth also invites us to explore how we understand these movements. For thousands of years, humans lived with earthquakes long before they knew why the ground shook. Whole cities would tremble, walls crumble, and the solid earth would suddenly feel unreliable. In the absence of scientific explanation, ancient peoples turned to stories. They imagined gigantic animals thrashing below the earth, gods expressing anger, or spirits shifting the world's foundations. These myths were not mere fantasy. They were ways to bring meaning to overwhelming experiences, to wrap fear in something understandable. But as centuries passed, observation and curiosity steadily replaced superstition. Scientists began noticing patterns, cracks in the ground, and the subtle ways landscapes revealed their histories. Eventually, the idea emerged that continents themselves drifted. This radical thought, once dismissed as impossible, evolved into one of modern science's most profound understandings: plate tectonics. The Earth, it turned out, was far more dynamic than anyone had imagined. Understanding how earthquakes work requires us to visualize the world in layers. Beneath the thin crust lies the mantle, a region of hot, slowly moving rock that behaves almost like a fluid over great stretches of time. Heat from deep within the planet creates currents in this mantle, pushing and pulling the crust above. These currents act like conveyor belts, guiding the plates on their long journeys across the globe. Sometimes the plates collide, other times they separate. In places where they pull apart, magma rises to create new crust, forming vast underwater mountain chains. In places where plates grind past one another, friction locks the edges until the tension snaps free. Each type of movement produces earthquakes, though their character differs depending on the nature of the boundary. As seismic waves ripple outward from a quake, they spread through layers of rock, passing through mountains, oceans, and continents. Some waves travel quickly, creating sharp jolts. Others move more slowly, rolling like ocean swells. Together, they create the complex pattern of vibrations we feel during an earthquake. Modern instruments capture these subtle motions, translating them into jagged lines on digital screens. From these lines, scientists can determine the quake's location, depth, and strength. Yet, despite all our knowledge, earthquakes retain an air of mystery. We can identify which regions are prone to shaking. We can estimate the likelihood of large events, and we can design buildings that sway instead of crumble. But we still cannot predict the exact moment a fault will slip. The Earth guards that secret tightly. What we can do, however, is listen. And the more closely we listen, the more the planet reveals. Small tremors, for example, can act as clues. They're like murmurs from the crust, signs that stress is gathering or that a fault is slowly adjusting. By studying patterns of these minor quakes, scientists can map hidden faults and identify where energy is building. These subtle signals help communities prepare, reminding them not to become complacent, even during long, quiet periods. Earthquakes also connect us to deep time. Every jolt we feel today is part of a sequence stretching back billions of years. Long before the first human ever looked up at the stars, the Earth was shaking, folding, and reshaping itself. Mountains rose in bursts of seismic energy. Valleys opened, oceans widened and narrowed. The ground we stand on carries the echoes of this ancient history. As we explore further in later parts, we'll look closely at seismic waves, faults, mythical beliefs, engineering marvels, planetary comparisons, and the ways cultures adapt to living with tremors. But for now, let the knowledge settle softly. The Earth beneath you is alive, endlessly shifting, endlessly creating, endlessly renewing. And while its movements may sometimes be sudden, they are also part of a much grander rhythm, the slow, steady heartbeat of a living world. To appreciate the story of earthquakes, it helps to imagine the Earth not as a solid, unbroken sphere, but as a puzzle made of immense drifting slabs. These slabs, our tectonic plates, cover the entire surface of the planet like pieces of a gigantic mosaic. Some pieces are the size of continents, others are mostly hidden beneath oceans, but all of them are constantly in motion. Slowly, steadily, patiently, like continents dreaming their way across the surface of the Earth. The idea that continents move is so familiar today that it can be hard to imagine how revolutionary it once was. For most of human history, the shape of the Earth's surface seemed immutable. Mountains appeared eternal, oceans unchanging, deserts timeless. Early philosophers believed the Earth was static, a perfect, unshifting stage upon which history played out. But nature was whispering clues all along, if only someone knew how to listen. Fossils provided some of those whispers. Identical ancient plants were found on continents now separated by vast oceans. Rock formations in South America match those in Africa like broken halves of the same object. The coastlines of distant lands seem to fit together like pieces of a puzzle. These clues converged into a stunning idea. The continents must once have been united. They must have drifted apart. This insight, proposed by Alfred Wegener in the early 20th century, was ridiculed at first. People asked what force could possibly move entire continents. It seemed impossible. But decades later, advances in ocean exploration revealed something astonishing. The seafloor was spreading. New crust was forming along underwater ridges, pushing the plates apart. At the same time, other regions were being swallowed back into the Earth's interior at deep ocean trenches. With these discoveries, Wegener's once dismissed idea evolved into the modern theory of plate tectonics. It became clear that the Earth was not fixed at all, but constantly reshaping itself. The planet's surface was alive with motion, driven by heat deep within the mantle, which churned and flowed like slow, molten currents. These currents tugged on the rigid plates above, guiding them into collisions, separations, and sideways glides. Each type of movement creates its own signature on the landscape. Collisions, the builders of mountains. Where plates converge, the crust compresses, rocks fold, fracture, and lift into high ranges. The Himalayas, for example, exist because the Indian plate is still pushing northward into Asia. Each year, the peaks rise ever so slightly. Though the motion is imperceptible to us, earthquakes here are frequent reminders of the ongoing collision. Separations, the birthplaces of new land. Where plates pull apart, the crust thins. Magma wells upward, forming new rock. Under oceans, this process creates underwater ridges stretching across thousands of kilometers. On land, the stretching creates rift valleys, long, deep depressions bordered by towering cliffs. The East African Rift is one such place where a new ocean may one day form. Sliding boundaries, the groaning edges where plates scrape past each other, tension builds silently. These transformed boundaries do not build mountains or oceans, but they are often the source of powerful earthquakes. The most famous example is the San Andreas Fault, a long tear across California where two massive plates grind alongside each other, locked together for years until they lurch in sudden, powerful slips. It is this lurch, the abrupt release of accumulated stress, that we experience as an earthquake. But earthquakes are far more than singular jolts. They are the outward expression of movements that have been happening for millions of years. Every quake, large or small, is the earth adjusting itself, realigning its pieces, accommodating the slow but unstoppable forces that shape the planet. As we unravel more of this story, we begin to see that faults, the breaks in Earth's crust where earthquakes originate, are not random scars but essential components of a dynamic system. They are the seams along which plates meet, the boundaries where motion expresses itself, and the openings through which we glimpse the immense forces that sculpt continents. What faults really are? Faults can be incredibly subtle. Some look like gentle ridges or faint lines across a field. Others are dramatic with cliffs, offset streams, and jagged scarps that mark ancient ruptures. Regardless of appearance, each fault is a record of past movements. With every slip, the crust rearranges itself. There are three primary kinds of faults, each tied to a type of plate motion. Normal faults, formed when the crust is being pulled apart. Reverse or thrust faults, formed under compression. Strike-slip faults, formed when blocks of crust slide horizontally past one another. The type of fault determines the type of earthquake, the shaking patterns, and the shape of the landscape afterward. Even within a single fault, the behavior can vary dramatically. Some segments creep quietly, moving little by little in steady increments. Others lock tightly, storing energy for decades before releasing it in a sudden, violent rupture. It is these locked sections that pose the greatest risk, because once they break, the shift can be dramatic. The slow build-up, before the break inside the crust, rock is not smooth. It is rough, jagged, full of friction. When two blocks of crust are pressed together at a fault, their irregular surfaces catch and hold. Strain accumulates like a stretched rubber band pulled almost to its limit. The rocks strain, bend, and deform. Eventually, the stress becomes too great, and the fault gives way. When it does, the release of energy radiates outward in waves. These waves are the true carriers of an earthquake's message. They travel outward in all directions, sometimes for thousands of kilometers, passing beneath oceans, through mountain ranges, and across continents. They cause the shaking we feel, the quick jolts, the rolling motions, the side-to-side sway. The Earth speaks in waves. Scientists categorize seismic waves into several types, each telling a different part of the story. Primary P waves, which compress and stretch the ground. Secondary S waves, which move the ground side to side or up and down. Surface waves, which travel along the Earth's exterior and often cause the most damage. Together, they form a sequence that lasts seconds or minutes, but tells a story millions of years in the making. When these waves are recorded by sensitive instruments, they provide immense insight. They reveal the quake's depth, the fault that ruptured, and even the structure of Earth's interior. With every earthquake, the planet offers scientists a momentary glimpse into places no human can ever visit. Layers of rock, thousands of kilometers beneath the surface. Deep time in every tremor. Earthquakes today are the continuation of a process that began long before humans appeared. They shaped the landscapes our ancestors walked across. They built the mountains that influenced climate, migration, and culture. They carved valleys that became cradles of early civilizations. Seen from this perspective, earthquakes are not isolated events, but vital parts of Earth's evolution. They are chapters in a geological story billions of years long, a story still being written. In the next part of this journey, we'll drift deeper into that story. We'll explore the structure of seismic waves, how they move, how they interact, and how they reveal hidden truths about the planet. We'll examine how scientists listen to the Earth, how cultures interpret its movements, and how humans have learned to coexist with an ever-shifting ground. For now, simply let this idea settle. The Earth is not still. It has never been still. And in every tremor, it expresses its ancient, ongoing need to change. As we continue this quiet journey into the heart of our restless planet, imagine the Earth as a vast communicator, a world that speaks not in words, but in vibrations. Every earthquake, no matter how small or distant, sends messages through the crust and mantle, echoing outward with information about its origin, its force, and the hidden architecture of the world beneath us. These messages travel in the form of seismic waves, subtle or powerful, intricate or simple, but always honest. They tell the truth about what has happened deep below, even when the event itself lasts only moments. When a fault ruptures, the Earth produces several kinds of waves simultaneously. They radiate outward from the point of rupture, the focus, and move through the planet's interior or along its surface. Though we often think of earthquakes as singular shakes, the reality is a layered melody of vibrations, each type of wave arriving at its own pace, shaped by its journey through various materials. Scientists have learned to interpret these waves much like musicians read notes or linguists decode languages. Let's explore this language, one wave at a time. Primary waves, the swift messengers. Primary waves, or P waves, are the first to arrive. They move the fastest, compressing and expanding particles in the direction of travel, much like sound waves moving through air. You could think of them as the Earth whispering before it speaks louder. Instruments detect them long before humans feel anything, giving scientists the first clues about distant seismic activity. Because they travel through both liquids and solids, P waves also help reveal where Earth's layers change. When they suddenly slow down, speed up, or bend, they indicate transitions between materials of different densities. By studying these shifts, scientists have mapped the boundaries of Earth's inner layers, including the outer core, a boundary discovered not through direct access, but through these subtle pulses. Secondary waves, the shaking heartbeat. Following P waves come the S waves, secondary waves that move more slowly, but create more pronounced motion. These waves travel perpendicular to their direction of movement, sliding particles side to side or lifting them up and down. The sensation they create can be disorienting, a kind of swaying or twisting that makes structures dance. S waves cannot travel through liquids, a fact that told scientists something profound. Earth's outer core must be molten. The absence of S waves in certain regions of the planet provided the evidence. The Earth was revealing a secret of its internal structure through the path its waves could not take. Surface waves, the rolling giants, last to arrive, but often the most powerful are the surface waves. Traveling along the crust like ripples across a pond, they can cause the ground to rise, fall, twist, or roll. These waves are responsible for much of the visible damage during a quake. They move slowly, but their effects linger, sometimes shaking the land for minutes. There are two primary kinds: love waves, moving side to side, Rayleigh waves, rolling like waves on the ocean. Together, they create the dramatic motion people associate with earthquakes. Earth's interior has a seismic map. Each wave, as it moves, interacts differently with the materials it encounters. Dense rock, liquid metal, partially molten mantle. All of them influence how waves travel. This allows scientists to build three-dimensional models of the Earth's interior without ever drilling more than a few kilometers into the crust. Earthquakes, in this sense, become tools. Every tremor maps a part of the world humans cannot touch. With enough quakes measured over decades, Scientists have created detailed images of the mantle's convection cells, the core's density, and the variations beneath continents. In a very real sense, the Earth reveals itself through shaking. How instruments listen to the Earth. Modern seismometers are remarkably sensitive. They can record motion so small that they are comparable to the width of a single atom. This sensitivity allows researchers to detect earthquakes that nobody feels, tiny adjustments in the crust that happen daily, even hourly, all over the planet. These small quakes may seem inconsequential, but they are crucial for understanding how faults behave. Patterns in microseisms help identify locked regions of faults, slow slip events, and creeping segments. Taken together, they form a detailed portrait of stress accumulation and release. Slow earthquakes, movements without shaking. Not all earthquakes announce themselves with dramatic motion. Some unfold over weeks or months, moving so gradually that no one notices. These are called slow slip events, or silent earthquakes. Instead of releasing energy in seconds, they release it gently, like a stretched rope, easing tension over time. Though we do not feel them, they can influence larger quakes. In some regions, a silent slip may transfer stress to a locked section of a fault, nudging it closer to a major rupture. In other cases, slow slip events relieve stress, making a large quake less likely. Scientists monitor these seismic murmurs carefully, knowing that the quiet moments can be as revealing as the loud ones. The mystery of earthquake precursors. Across history, people have looked for signs that an earthquake is coming. Animals acting strangely, unusual weather, lights in the sky. Countless stories have circulated, sometimes with kernels of truth, but often without reliable patterns. Modern science has searched for consistent precursors, changes in radon gas emissions, fluctuations in electrical conductivity, or swelling of the ground. While some correlations exist, none are reliable enough to serve as prediction tools. The Earth's crust is too complex, its faults too variable, the timing too chaotic. Instead, scientists focus on probability, forecasting where quakes are likely based on long-term patterns rather than predicting the exact moment. It is similar to weather forecasting, but with deeper uncertainties. Earthquake clusters and aftershocks. One of the most fascinating aspects of seismic behavior is how earthquakes come in clusters. A significant quake often reshapes stress in the region, triggering a series of aftershocks. These aftershocks can continue for days, weeks, or even years, gradually decreasing in frequency as the crust settles. Sometimes, a cluster precedes a major event. These are called foreshocks. But not all clusters have a main shock, and not all main shocks have foreshocks. Patterns exist, but they are inconsistent, reminding us again that the Earth does not operate by human expectations. The planet's rhythms, earthquakes, also follow long-term cycles. Some faults rupture roughly every few hundred years, a pattern determined through geological records. Sediment layers preserve old seismic events in the form of displaced strata, allowing scientists to estimate recurrence intervals. These cycles help predict where large quakes are overdue, yet the timing still varies by decades or centuries. The Earth moves according to its own rhythm, one we can study but cannot fully synchronize with. The sound of a distant tremor. If you were to listen to the Earth, truly listen, you would hear it humming. Seismologists have recorded the planet's constant background vibration, called the seismic hum. Even in the absence of earthquakes, The Earth vibrates faintly due to ocean waves, atmospheric pressure, and distant storms transmitting energy through the crust. This hum is peaceful, low, and continuous. It is the planet's breathing, quiet, steady, enduring. Cultural interpretations of a planet that moves throughout history, humans have created stories to explain earthquakes. In some cultures, a giant creature held the earth aloft, its movements causing tremors. In others, gods expressed displeasure through shaking land. Some believed that the earth floated on a cosmic ocean that occasionally churned with unseen forces. These myths, while scientifically inaccurate, reveal something profound. Humans have always lived with uncertainty. Before the tools of science existed, people sought meaning in mystery. And even now, with all our knowledge, we still feel a hint of that ancient awe when the ground moves beneath our feet. The role of science in a moving world today. Seismic networks span continents. Satellite systems measure ground deformation with centimeter precision. Subsea sensors monitor deep ocean faults. This vast web of instruments continuously listens to the Earth, gathering data, refining models, enhancing understanding. Our ability to measure earthquakes has never been more advanced, yet the planet remains unpredictable. And perhaps that is precisely what makes studying it so compelling. The blend of what we know, what we hope to know, and what still eludes us. As we move into the next part of our journey, we will look beyond waves and into the heart of faults themselves, their architecture, their layers, their behaviors, and their histories. The ground beneath us may feel solid, but its secrets run deep. Let your mind rest in that thought. Even silence carries meaning. Even stillness hides movement. And the earth always has more to reveal. Imagine standing on a landscape that looks perfectly ordinary. A field, a quiet valley, a hillside dotted with trees. Yet beneath that peaceful surface lies a hidden seam in the earth, a boundary where the crust has fractured and shifted countless times over millions of years. These invisible boundaries are faults, the places where Earth's rigid outer shell breaks, bends, drags, or slips as tectonic forces push and pull the planet's surface. They are the source of nearly every earthquake, the gateways through which Earth releases its accumulated tension. A fault is not a single crack. It is a zone, sometimes narrow, sometimes sprawling across kilometers, made up of crushed rock, layers of minerals, striated surfaces, and deep fractures extending far into the crust. Each fault is a history book, storing evidence of past movements, polished rock faces, offset layers, warped sediments, microscopic lines etched by grinding plates. When geologists study faults, they are reading the planet's autobiography, chapter by chapter, slip by slip. The anatomy of a fault zone. To understand how a fault behaves, imagine a giant book lying on its side. Each page is a layer of rock. A fault cuts through these pages diagonally, shifting one side upward, downward, or sideways relative to the other. But faults are far more complex than a single surface. Deep underground, a fault zone may include the primary fault plane, where the biggest movements occur, secondary fractures branching off like lightning bolts, fault gouge, soft clay-like material made from pulverized rock, breccia, rock fragments cemented by minerals formed during past slips, slickened sides, polished surfaces created as rocks slide over each other over thousands of years. Minerals like calcite, quartz, or clays fill the fractures, sealing some parts of the fault while leaving others rough and jagged. These differences influence how stress builds and releases. A smoother surface may creep slowly. A rougher segment may lock tightly until it finally breaks in a sudden quake. Locked versus creeping faults. Some faults move steadily, inch by inch, without generating noticeable earthquakes. These are creeping faults, and though they may cause minor cracking at the surface, they rarely produce destructive tremors. The movement is continuous, like the quiet slide of two boards rubbed together. Other faults, however, behave like rusted hinges stuck until immense pressure forces them open. These are locked faults, where friction prevents motion for decades or centuries. When they finally slip, the released energy can be enormous. Most major earthquakes come from these locked segments. The rupture begins at one point and races along the fault line at incredible speeds, sometimes faster than sound waves travel through rock. This sudden rupture releases energy that has been accumulating for generations. Fault systems, the planet's interconnected web, rarely does a fault exist alone. Large tectonic regions often contain entire networks of faults, each influencing the other. California's seismic system, for example, includes hundreds of faults connected to the San Andreas Fault. When one shifts, it can alter stress on the others, increasing or decreasing the likelihood of future quakes. This interconnectedness means that earthquakes often occur in clusters. A rupture in one area may redistribute forces, triggering movement elsewhere. It is a bit like pressing on one side of a bookshelf. The books shift, leaning into one another until the entire row rearranges. Where faults reveal themselves on the surface, faults express themselves in different ways. Offset streams that suddenly change direction, steep scarps, sharp cliffs created by vertical shifts, linear valleys, long depressions shaped by horizontal movement, split fences or roads offset by path slips, saturated soils, sometimes liquefied during shaking. Some faults are subtle, hiding beneath vegetation or soil. Others carve dramatic scars across landscapes, marking where the earth has shifted violently in the past. The deep extent of faults. Faults can extend astonishing distances. Some remain shallow, only a few kilometers deep. Others slice through the crust down to depths of 15-20 kilometers or more. Below that depth, rocks become too hot and ductile to fracture. Instead of breaking, they bend, absorbing stress like warm wax. This difference between brittle and ductile behavior explains why earthquakes occur only in the upper crust. The deeper parts of faults still play a role, though. They influence how stress travels upward, shaping the behavior of shallower segments. In some regions, fluids like water or carbon dioxide seep into faults from deep underground, reducing friction and altering how easily the fault slips. Fluids and earthquakes, a hidden influence. Deep within the crust, high-pressure fluids can act like lubricants. When they infiltrate faults, they reduce friction, allowing the rocks to slip more easily. This can trigger small tremors or even larger quakes, depending on the fault's condition. Natural processes move these fluids over long periods, but human activity can influence them too. In some areas, the injection or extraction of fluids, such as water, oil, or gas, has been linked to increased seismicity. This does not create new faults, but it can activate existing ones. How scientists study. Studying faults is like examining the scars of past injuries to predict future behavior. Geologists use many tools: trenching, where long ditches are dug across faults to expose layers of displaced sediment. Ground-penetrating radar which reveals buried structures without excavation. Satellite imagery detecting minute shifts in ground elevation. GPS networks measuring movements as small as a few millimeters per year. Seismic arrays listening for microquakes that reveal hidden fractures. These methods allow scientists to reconstruct centuries of fault activity. By studying soil layers, they can identify past surface ruptures, estimate their magnitude, and determine how often large quakes have occurred. The slow story, written in sediment. Imagine a valley floor layered like a cake. Each layer of sediment tells a story of flooding, erosion, wind deposits, or earthquakes. When a fault ruptures the surface, it disrupts these layers. Later, more sediment buries the disturbance, preserving it like a page in the planet's diary. Geologists carefully analyze these layers to reconstruct the sequence of ancient quakes, a field called paleoseismology. Through this work, they estimate recurrence intervals, often discovering that a major fault may rupture every few hundred years, though the timing varies widely. Why fault behavior is so unpredictable? Despite centuries of study, predicting exactly when a fault will slip remains impossible. Here's why. 1. Material differences. Some sections are smooth, others jagged. 2. Variable fluid pressures, which can raise or lower friction. 3. Stress transfer. Pressure changes caused by nearby quakes. 4. Chemical alteration. Minerals forming or dissolving within fault zones. 5. Temperature and depth variations, which change the rock's behavior. Each fault is a unique system with its own complex dynamics, making precise short-term prediction unrealistic. But long-term forecasting, identifying which regions are likely to experience large quakes, is increasingly accurate. The global distribution of faults are not distributed evenly across the planet. They cluster along tectonic boundaries, especially around the Pacific Ocean, creating the region known as the Ring of Fire. Here, intense tectonic activity generates the majority of Earth's largest earthquakes and volcanic eruptions. Other regions, though far from plate boundaries, can still host seismic activity due to ancient faults deep within the crust. These intraplate earthquakes are less common, but can be surprising and destructive precisely because the faults are old, hidden, and poorly understood. Fault zones as ecosystems. Interestingly, faults influence more than just earthquakes. They act as pathways for water, heat, minerals, and even life. Fault zones can host unique ecosystems where deep circulating fluids carry nutrients and warmth to the surface. Hot springs, mineral deposits, and geothermal fields often form along these zones. In this sense, faults are not only scars, they are arteries of the earth, transporting resources and shaping the environment. Living with faults, communities built near active faults learn to coexist with their restless neighbors. Some regions design buildings that sway safely. Others prepare emergency plans, develop early warning systems, or enforce strict construction codes. Awareness becomes part of the culture, a quiet understanding that the ground may one day move. This shared awareness does not create fear, but resilience. It reminds people that living on a dynamic planet requires respect, preparation, and knowledge. As we move into the next part of our exploration, we will step away from geology and look at how civilizations throughout history have responded to earthquakes through architecture, engineering, legends, and adaptation. Humans have always lived with a shifting earth, and their stories reflect that enduring relationship. For now, consider this thought. The ground beneath you is ancient but never idle. Faults, though hidden, shape the world more than we realize, and every quiet day above is supported by a world of movement below. For as long as humans have walked the earth, the ground has sometimes moved beneath their feet. These sudden motions, unexpected, powerful, impossible to ignore, left deep impressions on early societies. Without the scientific understanding we have today, ancient people interpreted earthquakes through story, symbolism, and myth. And as generations passed, these interpretations shaped culture, architecture, and attitudes toward the land. This part of our journey explores how humanity has responded to a world that occasionally shifts without warning, how we explained the unexplainable, adapted our buildings, cultivated resilience, and eventually learned to study the earth's trembling rather than fear it. When the world shakes without warning, to ancient civilizations, an earthquake was more than a natural event. It was a rupture in reality, a moment when the seemingly stable world betrayed a hidden instability. Walls that had stood for decades crumbled in seconds, streets split open, pillars fell, and the very idea of solid ground was shaken. Before modern science illuminated the causes of earthquakes, ancient societies reached for explanations rooted in the patterns they understood best: divine will, cosmic creatures, moral lessons, and the restless behavior of the natural world. Mythic interpretations. Across cultures, each region developed its own story, reflecting the values and beliefs of its people. Japan, the Namazu, the giant catfish. In Japanese folklore, a massive catfish called Namazu lived beneath the islands, trapped under the weight of a god. When Namazu thrashed, the earth trembled. The story captured something intuitive. The earth seemed alive, capable of sudden, violent motion. Even today, the imagery of Namazu appears in old woodblock prints depicting earthquakes. Greece, Poseidon, the earth shaker. To the ancient Greeks, the god Poseidon ruled not only the seas but also the shaking ground. Armed with his trident, he could strike the earth and unleash tremors. Temples dedicated to him bore titles linking him to earthquakes, reinforcing the belief that quakes were divine expressions. India, the elephant foundation of the world. In some Indian traditions, the earth was carried by elephants or held up by a cosmic serpent. When these creatures shifted or stretched, the earth shook. This belief offered a comforting idea. Earthquakes were not random, but tied to the motions of beings who supported the world. The Americas, the breathing earth. Some Native American traditions describe the earth as alive, constantly inhaling and exhaling. Earthquakes occurred when the planet adjusted its posture or shifted its weight. Rather than attributing quakes to punishment, these stories acknowledged Earth as a living entity with its own rhythms. Lessons hidden in legends. Though mythological explanations differed, many contained observations that match real geological processes. The Earth moves unexpectedly. Earthquakes recur over long periods. They come from deep below. They are connected to the structure of the world. Even without scientific language, ancient societies recognized patterns. Myths captured a sense of awe and respect for nature's power, a feeling still relevant today. Early architecture and earthquake survival. Over time, as communities learned from repeated quakes, architecture began to evolve. Some of the earliest earthquake-resistant features arose not from engineering theory, but through survival-driven trial and error. Examples include flexible timber frames in Japan, which swayed rather than shattered, interlocking stone blocks in Inca architecture, fitted so precisely that they could move slightly without collapsing. Lightweight roofs in certain Mediterranean regions, reducing the danger of falling debris. Layered adobe structures reinforced with organic fibers. These innovations emerged long before the science of seismology existed. They represented human intuition, observation, and practical wisdom forged through centuries. The Inca, masters of seismic architecture. One of the most remarkable achievements in ancient engineering is the precisely cut stonework of the Inca civilization. Their cities, built high in the Andes, sit in one of the most seismically active regions of the world. Yet many of their structures have endured earthquakes that destroyed more modern buildings nearby. The reason lies in their construction techniques. Stones were shaped to interlock without mortar. Slightly trapezoidal doorways and windows added stability. Walls leaned inward, reinforcing their strength. Foundation stones were set deep into the ground. When quakes shook the mountains, these stones moved like pieces of a puzzle, absorbing motion rather than resisting it rigidly. After the shaking stopped, they often settled back into place. Ancient Chinese seismoscope, the first earthquake detector. In 132 CE, Zhang Heng, a Chinese astronomer, invented one of the earliest devices for detecting distant earthquakes. His instrument used dragon-shaped vessels holding bronze balls. When seismic waves passed through the ground, one ball would drop into the mouth of a toad sculpture below, indicating the direction of the quake. Though simple by modern standards, this invention demonstrated a sophisticated understanding that earthquakes generate waves that travel through the earth. From mysticism to measurement, as civilizations advanced, curiosity replaced myth. Scholars began asking deeper questions. What causes the ground to move? Why do some regions shake more than others? Can earthquakes be predicted? How can communities prepare? Over centuries, these questions led to the birth of seismology, the science of studying earthquakes, the dawn of seismology. It wasn't until the 19th century that seismology emerged as a formal field. This shift was driven by improved scientific instruments, record keeping during quakes, a growing understanding of geology, mathematical modeling of the Earth. Researchers realized that earthquakes produce measurable waves. By tracking the arrival times of those waves at different stations, they could locate the epicenter. Soon, global networks of recording stations appeared, allowing scientists to detect quakes anywhere on Earth. The human relationship with uncertainty. Even with knowledge, earthquakes remained unpredictable. This uncertainty shaped the human relationship with seismic activity. Communities developed rituals for protection, calendars tracking past quakes, songs and stories teaching children how to respond, building customs that emphasized flexibility, cultural philosophies accepting the earth as dynamic. In many regions, earthquakes became woven into cultural identity, a shared understanding that life on a shifting planet requires adaptability. Modern engineering, designing for the unexpected today, architects and engineers draw from both ancient wisdom and cutting-edge research. The goal is not to stop earthquakes, an impossible task, but to allow structures to survive them. Modern earthquake-resistant designs include base isolation systems, where buildings rest on flexible bearings that absorb shaking, shock absorbers integrated into skyscrapers, diagonal bracing to support lateral loads, flexible frames that bend rather than break, lightweight materials that reduce collapse risk, damping systems that reduce sway. These innovations turn buildings into active participants during quakes, allowing them to move safely with the earth. Early warning systems, seconds that save lives. In some countries, advanced sensor networks detect the first waves of a quake, the fast but weak P waves, and issue alerts before the stronger S waves arrive. These warnings may grant only seconds, but those seconds can halt trains, close gas valves, alert surgeons, stop elevators at safe floors, give people time to take cover. A few seconds can mean the difference between chaos and protection. Earthquake culture. Living with a moving planet around the world, communities in earthquake-prone regions develop a shared culture of preparedness. It becomes part of daily life, not a source of fear, but of awareness. People learn how to secure furniture, where to take shelter, what supplies to keep ready, how to assist neighbors, how to rebuild when necessary. This culture of resilience turns seismic risk into a collective strength. The emotional landscape of earthquakes. Beyond the science and engineering, earthquakes affect people psychologically. The sensation of the ground moving, something we take for granted as stable, can be deeply unsettling. Yet communities recover, rebuild, and grow stronger. The emotional journey often includes initial shock, concern for loved ones, a surge of community unity, renewed respect for nature, re-evaluation of priorities. In many places, earthquakes become historical markers, events that shape cultural memory and collective identity. The balance between fear and understanding knowledge does not eliminate fear, but it reframes it. When we understand that earthquakes are not punishments or omens, but natural consequences of a dynamic earth, we gain perspective. We learn to replace helplessness with preparation, panic with awareness, and fear with respect. As we move into part 6, we will explore how Earth's shifting crust interacts with oceans, volcanoes, and the depths of the mantle, and why earthquakes are not isolated events, but pieces of a broader global system. For now, let yourself settle into this comforting realization. Humanity has always lived with earthquakes. We have learned from them, adapted to them, and even found meaning in them. And through knowledge, our resilience continues to grow. The world beneath our feet is far more dynamic than it appears. Although we live our lives on the solid crust, the forces responsible for earthquakes originate much deeper, in a realm far removed from sunlight, weather, and life. To understand why the earth trembles, we must descend, conceptually, if not physically, through layers of rock and heat, into the hidden engine of our planet. This part takes you into the deep interior of the earth, the mantle, the core, and the vast convective systems that power tectonic movement. Here, in the silent depths, beneath the crust, the story of earthquakes truly begins. The earth as a layered world. If you could slice the earth open like a fruit, you would find distinct layers, each with its own physical properties, temperatures, and roles in the planet's behavior. From the outside in, these layers are the crust, the thin, rigid outer shell, the mantle, a vast, slowly flowing layer of semi-solid rock, the outer core, a swirling sea of molten iron and nickel, the inner core, a solid metal sphere under immense pressure. Though we think of rock as static and unmoving, the mantle is constantly in motion, not fast like wind or water, but slow, like a glacier flowing over centuries. It is this sluggish movement that shifts continents and drives the creation and destruction of crustal plates. Mantle convection, the planet's hidden circulation. The mantle's movement is driven by heat rising from the core. Deep within the Earth, temperatures soar to thousands of degrees, creating powerful convection currents. Hot material rises toward the surface, cools slightly, and sinks again. A never-ending cycle of upwelling and descent. These currents act like conveyor belts for the plates above. Where mantle material rises, the crust stretches and forms new land. Where it sinks, the crust is dragged downward and recycled into the deep earth. This slow but relentless circulation is the engine behind tectonic activity. It is astonishing to think that earthquakes, volcanic eruptions, and mountain building ultimately trace back to the planet's internal heat, a source that has burned since Earth's formation billions of years ago. Where mantle upwelling shapes the surface, some of the most dramatic features on Earth owe their existence to mantle upwelling. Mid-ocean ridges, where new crust forms volcanic hotspots like Hawaii or Iceland. Rift valleys, where continents slowly split apart. In these regions, the crust thins and becomes more flexible. Earthquakes here tend to be shallow but frequent, reflecting the tension of a planet stretching itself open. Where mantle downwelling consumes the crust. In subduction zones, where one plate dives beneath another, the mantle pulls slabs of crust deep into the earth. This process creates deep ocean trenches, powerful volcanic arcs, some of the largest earthquakes ever recorded. As the descending plate sinks, it releases water and minerals that trigger melting in the mantle above, feeding volcanic eruptions. Meanwhile, the friction and pressure along the subduction interface can lock the plates together for centuries before they suddenly rupture in catastrophic megathrust earthquakes. Events like the 2004 Indian Ocean earthquake or the 2011 Tohoku quake in Japan originated in these zones, places where the Earth stores enormous amounts of stress. The mysterious transition zone between the upper and lower mantle lies a strange region known as the transition zone. Here, intense pressure changes the structure of minerals, converting them into new forms that behave differently. This region contains high-pressure minerals that do not exist near the surface, layers where seismic waves slow down or speed up, zones that may store vast amounts of water trapped within crystal structures. The transition zone acts as a boundary that influences how convection currents move. Some plumes rise straight through it, others spread out or stall, creating complex flow patterns that affect tectonic behavior above. Scientists believe this layer may also explain why some regions have persistent volcanic activity or unusually deep earthquakes. Deep earthquakes, tremors from the mantle. Most earthquakes occur in the crust, but some originate far deeper, 300 to 700 kilometers beneath the surface. These deep focus earthquakes are puzzling because rocks at those depths are expected to behave plastically, bending rather than breaking. Yet these quakes exist. They may be caused by transformations of minerals that suddenly collapse into denser forms, dehydration reactions, releasing trapped water. Stresses within subducting slabs as they bend and heat up. Though deep quakes rarely cause surface damage, they offer rare insights into the planet's interior, like echoes from a hidden realm. The outer core, a sea of liquid metal. Beneath the mantle lies the outer core, an immense layer of molten iron and nickel that moves chaotically. Its swirling eddies generate Earth's magnetic field, a force that protects the planet from solar radiation and enables compasses to work. Earthquakes cannot originate in the outer core because liquids cannot store elastic stress. However, seismic waves passing through this layer reveal its properties. P waves slow dramatically, S waves vanish entirely. These observations form the foundation of our understanding of the core's composition. The inner core, a solid world within a liquid sea. At the very center of the planet lies the inner core, a sphere of solid metal locked under unimaginable pressure. Although we cannot directly observe it, seismic data suggests it may rotate slightly faster than the rest of the Earth. It might contain distinct layers. It grows slowly as the outer core cools. Its crystal structure influences seismic wave behavior. The inner core is like a buried star, radiating heat outward, driving the entire geodynamic system. How all these layers shape earthquake behavior. Earthquakes are not isolated events. They are the final expression of deeper processes. Heat rises from the core. Mantle currents shift continents. Plate boundaries accumulate stress. Faults rupture to release that stress. Every tremor, from the faintest microquake to the most powerful mega thrust, is part of this colossal system of internal forces. The planet's cycles of destruction and creation over geological time. The deep Earth engages in cycles. Continents merge into supercontinents. Supercontinents break apart. Ocean basins open and close. Mountains rise and erode. These cycles, spanning hundreds of millions of years, are driven by mantle flow and core heat. Earthquakes are simply the localized temporary manifestations of these broader processes, the planet adjusting itself piece by piece. Subduction recycling, the Earth reorders itself. When old oceanic plates sink into the mantle, they carry water, sediments, carbon, minerals. These materials are transformed by heat and pressure, influencing volcanic chemistry and mantle evolution. The cycle is so efficient that oceanic crust is rarely older than 200 million years, while parts of continental crust have existed for over 4 billion years. This constant recycling shapes the long-term history of earthquakes. The hidden influence of temperature controls how rocks behave. Hot rocks bend and flow. Cold rocks snap and fracture. This is why shallow earthquakes can be so destructive. The crust is brittle at low temperatures. But deeper down, the increasing heat causes rocks to deform smoothly, preventing sudden failure. Temperature gradients create layers of varying strength, guiding fault behavior. Magma movement and volcanic earthquakes. In volcanic regions, earthquakes may not be caused by tectonic plates, but by rising magma. As molten rock forces its way upward, it cracks surrounding rock, creating swarms of small quakes. These volcanic earthquakes can signal impending eruptions, new magma chambers forming, shifting underground plumbing systems. Volcanoes and tectonics are deeply intertwined, both shaped by the same planetary forces. The role of water deep underground water, though subtle, can dramatically influence seismic behavior. In subduction zones, water carried by the sinking plate lowers the melting point of mantle rock, triggering volcanism. It also weakens minerals along faults, affecting rupture timing. Some deep earthquakes may be caused by dehydration reactions, where minerals release water as they transform, creating sudden pore pressure pulses. The global seismic system. Every earthquake affects the whole planet. Seismic waves travel around the Earth multiple times, gradually fading but offering scientists valuable data about the thickness of layers, the properties of minerals, hidden structures beneath continents. Each major quake acts like a tap on a drum, causing the Earth to ring faintly for days or weeks. Pulse points of the planet. Certain regions are exceptionally active because they sit atop major mantle features. The Pacific Ring of Fire, the East African Rift, the Mediterranean Belt, the Andes and Cascades volcanic arcs, Indonesia's complex plate boundaries. These areas serve as pressure valves for the planet, places where internal forces find expression. The deep Earth as a living system. Though it moves slowly, the mantle behaves in many ways like a living system. It circulates, it consumes and produces material. It transports heat, it reorganizes itself, it responds to stress. Earthquakes are simply the audible signs of this hidden vitality, a planet that never sleeps. Even right now, while you read these words, the interior of the Earth is moving. Plates glide a few centimeters each year. Mantle plumes rise, subducting slabs sink into the depths. Deep currents twist beneath continents. All of this happens in silence, unnoticed by human senses. But occasionally, the energy stored deep within reaches the surface as a quake. A reminder that our world is alive, dynamic, evolving. As we move into part 7, we will leave the deep interior behind and examine how earthquakes interact with oceans, how tsunamis form, and how the sea and the solid earth share a powerful, sometimes destructive relationship. For now, let this thought anchor you gently. Beneath the quiet ground lies an entire universe of motion. Invisible currents shape continents and oceans, and every tremor, no matter how small, is part of the grand conversation between Earth's layers. The ocean, vast and seemingly peaceful, holds within it a capacity for incredible force. Most days, its waves rise and fall in gentle rhythm shaped by wind, tides, and the pull of distant storms. But occasionally, the sea responds to something deeper, a shift in the planet's crust, far below the waves, where tectonic plates collide, slide, or descend into the Earth's mantle. In those moments, the ocean becomes an extension of the Earth's motions. A single rupture beneath the seafloor can send tremors through the water column, displace billions of tons of water, and generate waves that travel across entire ocean basins. These powerful waves, known as tsunamis, are among the most dramatic consequences of seismic activity. In this chapter, we explore how earthquakes interact with the ocean, how tsunamis form and travel, and how the sea and the solid earth are intertwined in ways that are both awe-inspiring and humbling. The ocean floor, a landscape. As dynamic as the continents beneath the water, lies a world of mountains, valleys, ridges, and trenches. The ocean floor is not merely a silent basin holding water. It is a tectonic landscape. Earthquakes beneath the sea are frequent because much of the world's plate boundaries lie under the waves. This underwater environment includes mid-ocean ridges, where new crust forms, subduction zones, where plates descend into the mantle, transform faults, where plates slide past one another, volcanic seamounts built by rising magma. Deep trenches, the lowest places on Earth, These submarine features are just as active, if not more so, than their continental counterparts. In fact, more earthquakes occur beneath the oceans than on land, though most go unnoticed by humans. Subduction zones, birthplaces of the most powerful tsunamis. The world's most destructive tsunamis originate from subduction zones. Here, one tectonic plate dives beneath another, locking and accumulating enormous strain. Over years and decades, the upper plate bends and flexes like a drawn bow. When it finally snaps upward during a megathrust quake, the seafloor is suddenly lifted or lowered. This abrupt vertical displacement moves the water above it, sending powerful waves outward in all directions. A large seafloor uplift can push millions of cubic meters of water upward in seconds, a movement equivalent to raising an entire city block of ocean. This is how tsunamis begin, how tsunamis differ from regular waves. Regular ocean waves are generated by wind. They affect the surface of the water and typically involve only the upper layers. Tsunamis, however, behave very differently. They involve the entire water column from surface to sea floor. Their wavelengths are incredibly long, up to hundreds of kilometers. In deep water, they travel at jetliner speeds, 500, 800 km/h. Their passage can be barely noticeable at sea. They compress and rise dramatically as they approach shallow coastlines. This distinction is vital. In the open ocean, a tsunami might appear as nothing more than a gentle swell, a meter high. A ship in deep water may barely feel it. But as the wave approaches land, the decreasing depth forces the wave to slow down and grow taller, sometimes reaching heights of 20, 30, or even more than 40 meters in extreme cases. The 5 stages of a tsunami. To understand tsunamis fully, scientists often describe their formation in 5 stages. 1. Initiation. A sudden displacement of the ocean floor, usually due to a megathrust earthquake, pushes water upward or downward. 2. Split. The displaced water splits into 2 waves. One travels outward across the ocean. The other moves toward the coast above the rupture. The outward wave can cross entire ocean basins. 3. Amplification. As the waves travel, their energy spreads but remains powerful. In deep water, they move swiftly with small height and immense wavelength. 4. Run-up. As the tsunami reaches shallower water, its speed decreases and height increases. The wave may rise as a towering wall or come ashore as a rapidly moving surge of water. 5. Inundation. The wave floods inland, reversing direction only after friction, with the land slows it. Multiple waves often follow, each potentially larger or more destructive than the last. Earthquake magnitude and tsunami potential. Not every large earthquake produces a tsunami. The key factors are location. Offshore quakes are more likely to trigger them. Depth. Shallow quakes displace the sea floor more effectively. Fault type. Vertical motion of thrust faults is far more tsunamigenic than lateral motion. Amount of displacement. The greater the shift, the larger the water movement. The most tsunamigenic earthquakes occur at subduction boundaries capable of producing megathrust ruptures above magnitude 8.5. Tsunamis from other sources. Though rare, tsunamis can also form from underwater landslides, volcanic eruptions, collapsing volcanic islands, meteorite impacts, glacial calving events. Some of the tallest waves in history came from landslides, not earthquakes. In 1958, a massive rockfall in Lituya Bay, Alaska, generated a wave that reached an astonishing 524 meters, the height of a modern skyscraper. This was a localized mega tsunami and though not representative of typical events, it demonstrates the ocean's potential power under extreme circumstances. The speed and scale of tsunami travel. Tsunamis can cross oceans in hours. The waves generated by the 2004 Indian Ocean earthquake reached Sri Lanka in 2 hours, Somalia in 7 hours, South Africa in nearly 12 hours. Their speed depends on water depth. Deeper oceans allow faster travel. Even more striking is that tsunamis can travel entire ocean basins without losing much energy. They can bounce off continental shelves, refract around islands, and reflect off underwater ridges. Natural warning signs. Though modern technology provides rapid alerts, nature also offers signs of an approaching tsunami. The ground shaking from a strong offshore quake, sudden withdrawal of water from the shoreline, a loud, unusual roar from the sea, rapid changes in water behavior. Communities familiar with these signs often respond instinctively. In some regions, traditional knowledge has saved thousands of lives. Modern tsunami warning systems. Around the world, networks exist to detect and warn coastal populations. Seismometers detect offshore quakes. Deep ocean pressure sensors track tsunami waves. Coastal buoys transmit real-time data. Satellites map ocean surface changes. Warning centers issue alerts within minutes. These systems can provide immediate alerts for nearby coasts. Hours of warning for distant locations. Lives are saved through preparation and communication. Earthquakes and coastal transformation. Tsunamis reshape coastlines. After a major event, scientists may find entire forests uprooted, coral reefs buried or exposed, lakes formed by saltwater flooding, beaches pushed inland, islands split or eroded, land uplifted or subsided. The coastline we see today is only a temporary snapshot in time. Subduction earthquakes and coastal uplift. In some regions, megathrust quakes lift coastal land by meters. In others, the ground drops, sinking permanently below sea level. These shifts happen within seconds, altering landscapes in dramatic ways. In Chile, Alaska, and Japan, tidal records, tree rings, and geological layers reveal cycles of uplift and subsidence connected to centuries of megathrust events, the ocean's memory. The sea preserves evidence of past tsunamis. In coastal lakes, marshes, and dunes, scientists find sand layers from ancient waves, marine shells transported inland, driftwood buried far above high tide, patterns of sediment matching known events. These records allow researchers to reconstruct tsunamis that occurred centuries or millennia ago. The emotional impact of tsunamis. Beyond their physical force, tsunamis affect people deeply. Communities describe the eerie silence before the wave, the feeling of disbelief as the ocean retreats, the awe of seeing water return as a wall or surge, the overwhelming sound of crashing debris, the strange calm after the waves recede. These emotional memories shape cultural narratives, rituals, and long-term resilience. Cultural stories of the sea's fury. Many societies have legends describing ancient waves. In the Pacific Northwest, stories speak of thunderbird battling whale, shaking the land and sending waves ashore. In Japan, old scrolls depict houses washed away by orphan waves. In Indonesia, oral traditions recount villages swept away by ocean spirits. These stories, though mythic, often reflect real geological histories. The interconnectedness of Earth and ocean earthquakes and tsunamis remind us that the solid crust and the ocean are part of a single system. The sea responds to movements of the Earth just as the Earth responds to the weight, pressure and circulation of the oceans. For instance, large tsunamis can redistribute ocean mass, affecting Earth's rotation slightly. Changes in sea level influence crustal pressure. Melting ice sheets can trigger seismic adjustments by lifting weight from the crust. The relationship is dynamic, constant, and reciprocal. Tsunami-resilient communities, regions that face frequent tsunamis, develop specific adaptations: elevated shelters, sea walls, evacuation routes painted on roads, mangrove forests used as natural buffers, schools teaching children automatic responses, drills conducted yearly. In some places, entire villages have been relocated to higher ground based on historical evidence. Nature's role in recovery. After a tsunami, ecosystems begin to heal in fascinating ways. Salt-tolerant plants colonize affected areas. Coral reefs regrow over decades. Birds and fish return to newly formed habitats. Mangroves recover, stabilizing sediments. Nature rebuilds slowly but steadily. Earthquakes, far from the ocean, can still influence it. Some inland quakes trigger landslides that splash into lakes or reservoirs, creating localized tsunamis. Others alter groundwater flow or change river directions. The Earth system is tightly interconnected. Even distant events can produce far-reaching effects. A planet linked by water and stone tsunamis are dramatic expressions of the deep relationship between Earth and ocean. They remind us that the planet is not divided into separate domains of land, water, and sky, but is a unified system where forces travel freely between realms. As we continue into Part 8, we will shift our focus from the ocean back to the land, exploring how earthquakes reshape mountains, influence climate over geological time, and play a role in the long-term evolution of continents. For now, let this calming thought settle. Even the most powerful waves begin with a single motion deep beneath the surface. The sea, like the Earth itself, responds to rhythms older than humanity, and every tremor beneath the waves is part of a story still unfolding. Even when the ground feels solid beneath our feet, the Earth's crust is never truly still. Mountains rise, valleys deepen, and plateaus shift in a continuous, imperceptible ballet. This ceaseless motion, driven by tectonics and shaped by earthquakes, tells a story written over millions of years, a story of immense power, patient persistence, and the slow artistry of geological forces. In this chapter, we explore how earthquakes interact with mountains, how landscapes are sculpted over time, and how the seemingly eternal peaks around us are, in fact, living monuments of the Earth's dynamism. The birth of mountains arise primarily at the boundaries of tectonic plates, where immense forces compress, stretch, or twist the crust. Two dominant processes create peaks. One, convergent boundaries, where plates collide, forcing the crust upward. Two, fault block and volcanic activity, where blocks of crust are lifted or magma pushes the surface skyward. Earthquakes frequently accompany these processes, relieving stress, fracturing rock, and sometimes triggering dramatic landslides that reshape slopes in minutes. Earthquakes as mountain sculptors. While erosion slowly wears down mountains over millions of years, earthquakes can instantaneously alter topography, triggering rock falls that clear steep cliffs, creating scarps, sudden cliffs, or steps on slopes, shifting ridgelines along fault plains, uplifting or lowering entire sections of a plateau. In this sense, mountains are both born and continually reshaped by the pulses of seismic energy traveling through the crust. faulted peaks and folded valleys. Mountain ranges are often complex assemblies of folded strata and faulted blocks. Compression forces rock layers to buckle into folds, while fractures allow blocks to slip past each other. Earthquakes trace these fault zones, highlighting where energy is stored and released. In the Himalayas, for instance, the collision of the Indian and Eurasian plates forces the crust upward at rates of several millimeters per year. Large earthquakes occur along deeply buried thrust faults. Each rupture subtly reshapes peaks, ridges, and valleys. Over millions of years, these incremental changes add up to the dramatic landscapes we admire today. Landslides and earthquake hazards in mountains are inherently fragile. Earthquakes can destabilize slopes, triggering landslides that cascade down valleys. Some of these landslides travel tens of kilometers from their source, move with incredible speed, transforming rock into a flowing mass, block rivers, creating temporary lakes, destroy vegetation, homes, and infrastructure. The 2008 Wenchuan earthquake in China illustrated this vividly, where hundreds of landslides reshaped entire valleys in a single event. Earthquakes and river dynamics. Seismic activity also alters rivers. Faulting can divert streams, raise or lower riverbeds, trigger damming and lake formation, increase sediment loads downstream. Over time, repeated earthquakes can profoundly influence the hydrology of mountain regions, creating new channels, waterfalls, or sediment plains. Seismic shaping of plateaus. High plateaus, like the Tibetan Plateau, experience earthquakes that subtly adjust their elevation. Though less dramatic than landslides, these movements redistribute stress across vast areas, gradually sculpting the landscape. Earthquakes can elevate plateau surfaces by meters in moments, cause slow creeping adjustments along fault zones, influence glacial movement in regions where ice covers high terrain. The plateau is not a static surface. It breathes and shifts with the Earth's internal forces. Earthquake-induced volcanism. In mountain regions are also prone to volcanic activity, often linked to deep tectonic movements. Subduction zones beneath mountain belts provide magma pathways. Earthquakes can trigger magma ascent, minor eruptions, gas release, hydrothermal activity. These volcanic events interact with seismic energy to further reshape terrain. Earthquake cycles in mountain belts. In mountain regions, earthquakes follow long-term cycles. Energy accumulates slowly along faults. A major earthquake releases that energy. Aftershocks adjust surrounding faults. Stress gradually builds again. This cycle explains why some mountain ranges experience periodic, catastrophic quakes interspersed with long periods of relative calm. The relationship between uplift and erosion. Earthquakes uplift mountains, but erosion works tirelessly to wear them down. Rain, wind, glaciers, and rivers steadily remove material, transporting it downstream. The balance between uplift from tectonics and reduction from erosion dictates the ultimate height and shape of ranges. In regions of active tectonics, mountains grow faster than erosion can remove material. In older, tectonically quiet regions, erosion dominates, creating rounded peaks and valleys. Earthquakes contribute bursts of sudden change that complement slower, erosional processes. This interplay ensures that mountains remain dynamic landscapes, always in motion. Seismic shadows and hidden faults. Not all faults are obvious on the surface. Some remain hidden, producing earthquakes without leaving visible scars. In mountain regions, these concealed faults can trigger unexpected tremors, cause rock slides on otherwise stable slopes, remap drainage patterns after a sudden rupture. Modern seismology, including GPS and satellite measurements, helps reveal these hidden fault systems, providing insight into potential hazards. Glacial interaction with seismicity. In high mountains, glaciers exert immense weight on the crust. As glaciers melt, the crust slowly rebounds, a process called post-glacial rebound. This adjustment can trigger earthquakes along existing faults, redistribute stress across mountain belts, influence long-term landscape evolution. The retreat of glaciers, accelerated by climate change, may subtly increase seismic activity in some mountain regions, earthquakes and rock formation. Repeated seismic events contribute to the formation of specific rock features. Breccia, broken rock fragments cemented together along fault zones. Fault gouge, fine pulverized material from sliding faults. Slickened sides, polished surfaces etched by frictional movement. These features are more than geological curiosities. They preserve the history of earthquake activity, offering clues to past magnitudes and frequencies. Mountain ecosystems and seismic change. Earthquakes influence ecology. Triggered landslides create new habitats. Altered rivers form wetlands. Rockfalls provide niches for plants and small animals. Floods reshape soils and nutrient distribution. Thus, seismic activity contributes to biodiversity, even in seemingly destructive ways. Cultural adaptation in mountain regions. Human societies have long adapted to living among mountains prone to earthquakes. Settlements are often located on stable terraces. Traditional architecture includes flexible timber structures. Ancient trails and irrigation systems accommodate shifting terrain. Oral traditions warn of seismic hazards. These practices reflect deep observation and coexistence with dynamic landscapes. Historical examples of mountain earthquakes. The 1906 San Francisco earthquake along the base of the Coast Ranges reshaped ridges and valleys. The 2005 Kashmir earthquake in the Himalayas caused landslides, altered river courses, and uplifted peaks. The 2015 Nepal earthquake, which fractured slopes and devastated towns while changing mountain topography. In each case, the mountains themselves responded alongside human settlements. Earthquakes and mountain weathering. Seismic shaking accelerates weathering. Exposed rock surfaces crack. Soil becomes unstable. Water infiltrates fractures, speeding chemical weathering over centuries. These processes contribute to the sculpting of cliffs, canyons, and alpine valleys. The poetry of mountains in motion. Though earthquakes can be destructive, they also remind us that mountains are alive, growing, shifting, and evolving. The peaks we admire are not eternal monuments, but dynamic formations shaped by deep forces and fleeting events, molded over eons by both violent and subtle energy. Each summit bears a history of stress and release. Every valley reflects the slow interplay of uplift and erosion. Rivers and glaciers trace the invisible hand of tectonic adjustment. This perspective transforms mountains from static scenery into ongoing narratives of Earth's restless energy. While mountains rise and oceans shift, earthquakes also remind us that the world operates on timescales far beyond human life. From the faintest tremors to catastrophic megathrust events, seismic activity is the Earth's language, a subtle pulse that communicates the planet's ongoing adjustments, stresses, and releases. This chapter explores how human societies perceive, adapt to, and coexist with these rhythms over centuries and millennia, emphasizing lessons that extend beyond individual events to the broader context of life on a dynamic planet. The scale of time. Earthquakes operate across a vast spectrum of temporal scales. Microquakes, nearly continuous, often imperceptible, releasing small amounts of energy. Moderate quakes occur every few years or decades in active regions. Megathrust events, rare, devastating, and sometimes centuries apart. Understanding this temporal variability is essential. While humans live in decades or centuries, the Earth operates on millions of years. This perspective allows us to see earthquakes not just as disasters, but as natural expressions of planetary evolution. Patterns hidden in history. Historical records and geological evidence reveal long-term seismic patterns archaeologists and geologists study. Ancient ruins affected by earthquakes, sediment layers disrupted by shaking. Written accounts describing tremors, tree rings damaged by shifting slopes. These patterns often suggest that earthquakes, though unpredictable in timing, follow recurring cycles influenced by tectonic forces. For example, coastal Japan shows evidence of repeated megathrust earthquakes every 300 to 500 years. Subduction zones in Chile have produced massive quakes every 200-300 years. Ancient sites in the Mediterranean reveal cycles of uplift and collapse. Recognizing these patterns helps societies plan, adapt, and anticipate risk over generational timescales. Human engineering and earthquake adaptation civilizations have always sought to live alongside seismic activity. Over centuries, they developed ingenious strategies. Ancient construction. Inca stonework. Interlocking blocks absorb shaking. Japanese pagodas. Flexible timber structures sway without collapsing. Roman amphitheaters and aqueducts. Careful engineering reduced structural vulnerability. Modern advances. Seismic base isolation. Buildings sit on flexible bearings to absorb tremors. Damping systems reduce sway in tall structures. Shock absorbers and reinforced frames increase stability. Urban planning. Avoiding construction directly atop known fault lines. Engineering solutions represent humanity's ability to read Earth's signals and respond with both creativity and foresight. Societal memory of earthquakes. Communities develop collective memories of seismic events through oral traditions, rituals and ceremonies, written histories, monuments and markers. For example, in Nepal, centuries of seismic events have informed construction practices and temple placement. In Chile, long-term awareness of subduction zone hazards has influenced urban design. In the Pacific Islands, legends of massive waves guide evacuation knowledge. This cultural memory often saves lives by embedding preparedness into daily routines. Earthquake-induced environmental change. Earthquakes reshape more than human settlements. They subtly or dramatically affect ecosystems. Landslides create new habitats. Rivers alter their courses, forming wetlands or lakes. Soil liquefaction redistributes nutrients. Seismic uplift modifies coastlines and river deltas. Over decades, centuries, and millennia, these changes influence plant succession, animal migration, and ecological diversity. Earthquakes, in this sense, act as ecological sculptors, altering landscapes that host life. Tectonic cycles and climate interactions. Earthquakes are intertwined with other planetary processes. mountain uplift influences wind and precipitation patterns. Subduction zone activity affects volcanic CO2 emissions, impacting climate. Earthquakes can trigger landslides that alter sediment transport to rivers and oceans, affecting nutrient cycles. These interactions highlight the profound interconnectedness of Earth systems, revealing that seismic activity is not isolated, but part of a global dynamic network. Psychological and cultural responses. Earthquakes have long shaped human thought, belief, and emotion. Fear and reverence. Tremors remind humans of natural power, resilience, and ingenuity. Societies develop survival strategies. Myth and legend. Stories encode geological observations for future generations. Art and architecture. Expression reflects both awe and adaptation. The psychological imprint of seismic activity demonstrates that earthquakes influence human culture as profoundly as landscapes. Global seismic networks today, science allows humans to monitor Earth's pulse continuously. Modern seismic networks track microquakes invisible to humans, map fault systems worldwide, measure tectonic plate movement in millimeters per year, provide early warning for tsunamis and large quakes. These networks are humanity's way of listening to the planet, translating subtle signals into knowledge and protective action. Predictability versus uncertainty. Despite advanced monitoring, earthquakes remain fundamentally unpredictable in timing. We can identify active faults and likely zones. We can estimate recurrence intervals. We cannot predict the exact moment a rupture will occur. This uncertainty is a reminder that the Earth is an evolving system. Respect, preparation, and adaptability are more valuable than attempts at absolute prediction. The interplay of small and large events. Seismic activity is continuous, with small events often preceding or following larger ones. Scientists study foreshocks, small quakes that sometimes precede major ruptures. Main shocks, the primary rupture event. Aftershocks, adjustments in surrounding faults after the main quake. These patterns illustrate how energy moves through the crust, akin to the circulation of fluids or vibrations through a flexible structure. Even subtle microquakes provide clues to the larger tectonic picture. The human perspective living on a shifting planet requires both humility and ingenuity. Earthquakes remind us that stability is temporary, risk is inherent in certain landscapes, preparedness saves lives. Observing natural patterns allows informed decisions. Communities that integrate geological awareness into culture and planning exhibit resilience that spans generations. Earthquakes as agents of renewal. Though often destructive, earthquakes also foster renewal. Create fertile valley soils from disrupted rock and sediment, form lakes that sustain new ecosystems, trigger erosion that redistributes materials for agriculture, reshape mountains and coastlines, creating new habitats. From this perspective, earthquakes are not merely disasters, but integral components of Earth's ongoing creative process. A long-term view. Human lifespans are brief, but the Earth's history stretches across billions of years. Viewed this way, earthquakes are small pulses in a vast continuum. Each event contributes to the sculpting of landscapes. Mountains, rivers, and oceans record the cumulative effect of countless quakes. Humanity is part of a long-term adaptation process to planetary rhythms. Understanding this long-term view cultivates respect for natural processes and patience for change. As we reach the final chapter of our journey through earthquakes, the mantle, oceans, and mountains, it is time to step back and see the Earth as a whole, a dynamic, living planet whose surface pulses with hidden energy. Earthquakes are not isolated events. They are expressions of the Earth's inner mechanics, whispers from the depths, and sometimes roaring signals of transformation. This final part reflects on the relationship between humans and the Earth, the lessons we carry forward, and the delicate balance of awe, respect, and knowledge. The Earth as a dynamic system. The planet's crust floats atop the slowly moving mantle, stretching, compressing, and bending under forces that are ancient and persistent. Beneath the surface, mantle convection circulates heat, driving plate tectonics. Subduction zones recycle oceanic crust and trigger megathrust earthquakes. Deep mantle plumes rise to the surface, fueling volcanic activity. Ocean basins and mountain belts interact with seismic events, shaping landscapes over millions of years. All these processes are interconnected, forming a planetary system that is constantly adjusting, evolving, and occasionally erupting with energy. Earthquakes, the pulse of a living planet. Earthquakes act as the Earth's heartbeat. Small tremors are the whispering pulse, barely noticeable. Moderate quakes are the rhythmic adjustments of strain release. Massive megathrust events are the surges, moments when stress accumulated over centuries is discharged. By observing these pulses, scientists have learned to read the Earth, tracing its rhythms, identifying fault zones, and predicting long-term patterns, even if precise timing remains elusive. The dual nature of earthquakes. Earthquakes embody a dual nature. They are both destructive and creative. Destructive. Lives are lost, buildings collapse, and ecosystems are disrupted. Creative. Landscapes evolve, soils rejuvenate, new habitats are formed, and mountains are sculpted. In this way, earthquakes are an essential part of the planet's ongoing narrative, agents of change in a constantly transforming world. Human adaptation, coexistence, and resilience. Humans have always responded to seismic forces with ingenuity and adaptation. Architectural innovation, from Incan stone masonry to Japanese timber construction to modern base-isolated skyscrapers. Cultural knowledge, oral traditions, ritual practices, and historic accounts preserve awareness of seismic hazards. Urban planning, evacuation routes, resilient infrastructure, and hazard mapping. Early warning systems, real-time detection of tremors, and tsunami alerts. By learning to live with earthquakes, humans have transformed vulnerability into resilience, turning awareness into survival. The ocean's role in the planetary story. The oceans respond to seismic shifts with tsunamis, waves that travel thousands of kilometers. Tsunamis redistribute energy from seafloor ruptures. Coastlines are reshaped, sometimes permanently. Marine ecosystems are temporarily transformed, allowing new ecological growth. Water and stone are not separate. They are interconnected. The sea mirrors the movements of the earth, carrying messages from the depths to distant shores. Mountains, as living testaments. Mountains, rising over millions of years, are sculpted continuously by earthquakes, erosion, and tectonic forces. Faults and folds record the history of stress and release. Rock slides and uplift reshape ridges and valleys. Glacial activity and erosion interact with seismic adjustments. Every peak and valley is a living record of Earth's internal energy, a monument not to permanence but to constant change. The invisible forces beneath, even where humans cannot see, the Earth's interior pulses with life. Mantle currents circulate heat. The outer core generates magnetic fields. The inner core stores energy and grows slowly, influencing convection. Deep earthquakes reveal the hidden mechanisms that shape the surface. Earthquakes, in this context, are only the visible tip of a vast, hidden system of forces. Cultural, emotional, and scientific lessons. Earthquakes teach humanity multiple lessons. 1. Respect for nature, understanding the power of processes beyond human control. 2. Patience and long-term thinking. Geological timeframes dwarf human lifespans. 3. Ingenuity and adaptability, how cultures innovate in response to hazard. 4. Interconnectedness. Earthquakes, oceans, mountains, and humans exist in a shared system. 5. Balance of knowledge and humility, awareness without arrogance. These lessons emphasize the coexistence with a dynamic planet requires observation, preparation, and reverence. The beauty in motion. Beyond danger, earthquakes reveal beauty. Subtle shifts realign rivers and valleys. Landslides reveal hidden rock strata. Coastal uplift uncovers ancient marine fossils. Mountains rearranged by seismic pulses display the artistry of geologic time. Earthquakes are a reminder that motion, change, and adaptation are inherent in the natural world. Earthquakes and the continuum of life. Every earthquake, from a faint tremor to a mega thrust, is part of a continuum. Microquakes lubricate faults and release small stress. Larger events restructure landscapes. Over millennia, these pulses allow life to evolve and adapt. Humans are observers and participants in this ongoing story, learning lessons about resilience, ingenuity, and patience. A final reflection. Take a moment to consider the ground beneath your feet. It is solid, yet dynamic. It has absorbed countless tremors, carried mountains, guided rivers, and supported generations of life. Earthquakes are part of this living system, not anomalies, but essential expressions of the planet's ongoing evolution. We have traced their origin from deep mantle currents to surface ruptures, explored their interaction with oceans, mountains, and human society, and glimpsed the hidden processes that shape continents and ecosystems. In doing so, we gain perspective, a sense of connection to the vast, complex, and beautiful world beneath and around us. Closing thoughts. The earth moves in quiet pulses and sudden shocks. Every tremor is a note in a planetary symphony. Human life is fleeting, but resilience and awareness create continuity. Knowledge, observation, and respect allow us to coexist with seismic forces. Mountains, oceans, and plains bear witness to the timeless rhythm of motion. As we conclude this journey, let the gentle awareness of the Earth's pulse settle into your mind. Its energy is vast, ancient, and unceasing. And yet, with understanding, preparation, and respect, humanity finds its place in harmony with a living, breathing planet. The sleepy geographers whisper. Finally, as the world settles into its natural rhythms, remember, tremors are not enemies, but messages. Mountains grow slowly, oceans respond, and the crust adjusts continuously. Humans, aware and adaptive, are part of this intricate web. Close your eyes, breathe deeply, and imagine the earth breathing beneath you, a planet alive dynamic, and endlessly fascinating. Let this understanding carry you into calm reflection and restful sleep, gently aware of the subtle pulse of our home, the earth,